Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, ladies and gentlemen. My name is Rasha Al-Ahmad, and I'm Chief Strategic Planning at Bahrain Space Agency. It is our pleasure to welcome you all today to the workshop, organized in collaboration with Eartheye Space. The workshop title is Seeing the Invisible: Applications for Infrastructure, Agriculture, and Environmental Monitoring. I'm sure you know that satellite-based advanced remote sensing technologies are transforming how governments monitor, plan, and protect national assets. This specific workshop introduces how different techniques such as hyperspectral imaging, shortwave infrared, and thermal infrared data from space reveal invisible insights that are critical for evidence-based policy and strategic planning. We will first start with short introductions about Bahrain Space Agency and Eartheye Space, followed by the technical part of the workshop that is split into 3 sections. Firstly, how satellite different remote sensing technologies work, comparative advantages against each one of them, and finally, real-world applications that are tailored to the Kingdom of Bahrain. The questions and answers are kept to the end of the workshop, so I advise if anyone has any question, please type it in the Q&A box in the top corner of the screen. So, allow me to quickly introduce Bahrain's space ambitions and efforts. The agency was established by a royal decree in 2014 to achieve His Majesty's vision in the space field, that is, achieving presence in space and utilizing space for the comprehensive and sustainable development of the kingdom. The core values and principles that we adhere to while achieving this vision are service, excellence, cooperation, and innovation. We have identified 3 strategic priorities: space research in upstream and in downstream, satellite services, specifically Earth observation data and analytics, and in the future, Earth observation ground stations, and third, design, development, and launch of small satellites and payloads. We have 7 strategic goals as part of our current strategic plan 2024-2028, and it's our 3rd cycle, by the way. Firstly is developing national cadres through space education and outreach initiatives targeting different segments of the society. Second is constructing a sound infrastructure to support the growth in the national space sector. And here this includes establishment of assembly and integration and testing facility of small satellites and components, establishment of ground stations and advanced laboratories for processing and analyzing satellite data and imagery. Our 3rd goal is supporting, developing, and encouraging space research and innovation. Our 4th is providing satellite data and analytics to fulfill national needs and, of course, solve challenges that contribute to the comprehensive and sustainable development of the kingdom. Our 5th is establishing relationships of cooperation to achieve joint projects, knowledge transfer, reduce mission costs and risks. Our 6th goal is a new goal that was added in this strategic cycle, which is creating a new space sector that contributes to economic prosperity and diversification. This mainly is to stimulate the private sector, SMEs, and entrepreneurs to enter the space sector. And finally, regulating space activities at national level through the announcement of national space law and, of course, joining international space treaties. In the following slides, I'll just touch upon how we achieve these goals and some of our accomplishments so far. For building capabilities, we have organized postgraduate scholarship opportunities in the UK and UAE. We have worked on projects for capacity building to achieve knowledge transfer. I'm sure you're aware of Light 1, and we have also worked on other small satellites like Dubisat in UAE. We have offered specialized training courses, such as in Netherlands, Twente University on downstream data analytics, for example, ISRO's UNATI program, St. Petersburg University. We have collaborated for curriculum integration with the Ministry of Education to try to embed space subjects in the national curriculum. We have offered on-job shadowing in the UAE and the Kingdom of Saudi Arabia. We have organized internships and mentorships opportunities at national level for university students and youth. We have organized many stakeholders workshops, such as this one today. And finally, we have worked on practical mission experience that resulted in launching our first national satellite, Al-Mundhir. This was the launch of Light 1, the first Emirati Bahraini 3U satellite launched in 2022. Its main objective was capacity building, and it also had a scientific objective to it. Our second and fully national satellite is Al-Mundhir, that was launched similar to our time this year. It was launched last year in 2025. It's our first 3U Bahraini satellite. It included 4 fully in-house developed payloads. Its main purpose was capacity building, and it also achieves Earth observation capabilities. This was the first process image captured by Al-Mundhir satellite presented to His Majesty the King. For space education and outreach, we have organized many events, local competitions, workshops. We have hosted many international space events like the annual Space Apps Hackathon, the International Space Forum in 2024, Space Medicine Workshop in 2025. We have hosted or organized alongside the Bahrain International Air Show the Space Forum that takes place every 2 years, space camps, whether in person or online during the summer. And finally, we are active on social media channels and our websites, where we continuously post space articles and updates on latest trends and technologies. For our second goal, that is constructing a sound infrastructure, we have partially established the lab to process and analyze satellite imagery and data with necessary hardware, software, acquiring imagery and data, building capacity of our lab team. We are yet to establish an advanced ground station for receiving satellite data and satellite operations and control, and establishment of an assembly integration and testing facility. These are hopefully in the pipeline. For the third goal, and to encourage space research, we have published more than 90 publications in well-known conferences and magazines. 50% are in collaboration with external entities. We have worked on joint research projects, like with the University of Leicester on the CO2 SAT project. And the Bahrain Space Agency participates as space research mentors under the International Astronautical Federation on an annual basis, where we mentor young professionals and students. For this specific goal, we have completed a government needs analysis of space information and Earth observation data. We continuously refine those requirements through meetings, different stakeholders. We have worked on technical skills of lab team. We have partially established the lab, as I've mentioned earlier. We started introducing services as part of our data analysis center to fulfill stakeholders' need. We are yet to initiate a project to build and launch an Earth observation high-resolution satellite to fulfill national needs. And these are some of our completed projects at the lab that we have worked along with our stakeholders, trying to fulfill their needs, such as a greenhouse count, mangroves monitoring and carbon sequestration, soil moisture and salinity, and other important studies. We have partnered with many space organizations and research centers. The Kingdom is a member of relevant international space organizations, and we have engaged in many projects with international partners, and these are some of our projects that are a result of our strong partnership. Light 1, you are aware, is the first Bahraini Emirati satellite that was launched. We have worked on the Arab satellite 813 for climate change monitoring. It was launched Q4 last year. We have worked on a payload for point source emission monitoring of CO2 from space alongside partners from the UK and many more. And of course, I'm very proud to mention two specific projects, lunar missions that we are engaged in. So we are currently working on a lunar rover payload in collaboration with Markaz Mohammed bin Rashid. For international recognition, we have received more than 17 international awards, and we have obtained many leading international positions. These are some of them. We are currently having the role, we are chairing the United Nations Scientific and Technical Subcommittee for the year 2027. Sheikh Hissa Al Khalifa is the second vice president of COPUS, the committee for 2025. Ms. Amal Al Bin Ali is vice president of the International Astronautical Federation for 3 years. And I am chairing the Arab Space Strategy Committee for developing the first Arab space strategy under the Arab Space Cooperation Group. Finally, for governance and policy, as you know, this happened over phases. Firstly, the establishment of the agency through a royal decree. Then the national space policy was announced in 2018. The first national space strategy for 5 years was announced in 2019. We have signed 3 of 5 main international space treaties under the UN that govern activities in the peaceful exploration and use of outer space. And we are currently in the phase of drafting our national space law. It is in its final stages. Thank you for allowing me to introduce the agency. I will leave the floor for experts from Eartheye Space. Mr. Shankar will first start and then followed by colleagues. Mr. Shankar.
Thank you, Rasha. All right. Assalamu alaikum. Let me see if I can bring up this and share. Where is my... Okay. Are you able to see my screen?
Yes, we can.
Perfect. Great. All right. Okay, so we are talking about, as we discussed as part of the agenda, new type of capability to sense the Earth from space. And I think you're all very used to sensing the Earth from space with optical. Most of you, at least some of the agencies that I've interacted with when I was in Bahrain a couple of months ago at the Geospatial event, wherein also I met with BSA. We talked about multimodal, multi-sensor capability in Earth observation. And what I found was most Bahraini users were using optical, predominantly multispectral, potentially 3 to 8, 10 bands. And we talked about the capabilities that exist today with hundreds of bands of hyperspectral, shortwave infrared, thermal infrared, and many more. So the discussion turned into a session like this to talk about, as optical is very good for seeing the visible, how do you see the invisible with narrow bands, narrow wavelengths, multi-bands, hyperspectral data. And in this continuum, we will also talk about thermal infrared as part of that conversation. So today's discussion, I don't want to call it a workshop, it's a discussion, so please feel free to ask questions. I know Rasha said it's at the end of the talk, so we'll wait. That's the protocol set. And so we'll talk about the next sort of 45 minutes. How do you get awareness of Earth from space, but with these sensors, particularly for infrastructure monitoring, agriculture, and environmental? So we prepared some use cases, but before we get to the use cases, which my colleague will present, I'll set the context about why this matters for Bahrain. So as I learned about Bahrain's 2030 vision, I think it's very ambitious and very achievable. There are lots of different capabilities being used to spearhead that, but we are not going to be talking about how that vision can be realized from space. What are the kind of capabilities exist from space to achieve that vision faster, better, cheaper, if I can put it that way, and potentially safer, right? So traditional monitoring methods in monitoring infrastructure or agriculture, productivity, yield, or environmental, they are good, but they have these perennial problems about of line of sight, weather dependent, and they're fragmented data sources, and you have to have the periodic inspections. And it's fundamentally, the problem is it's heavily human dependent, right? So human resource dependent. And how do you then turn that into something that you can continuously have visibility of, rather than leaving to humans? So, for example, underwater water leaks, right? So how do you detect early crop stress? So, for example, dates are an important crop in Bahrain, in the Middle East. How do you detect early crop stress, soil degradation, or heat islands? It's a very hot area. How do you identify various heat islands within the kingdom itself because of various aspects, including construction, type of materials used, environmental considerations around the area, and coastal changes, and flood. So as I understand, flood is one of the major disaster events in Bahrain. What happens to post-flood pollution management? So these are all various issues that can degrade the environment, that can degrade the agriculture productivity, but also affect the infrastructure. So how do we get early warning from the kind of sensors that are capable of providing early warning than that you might be used to already? So that's going to be the theme of the conversation today. So we're going to talk about two specific sensors. One is a continuum of the other. So we're going to talk about hyperspectral and shortwave infrared, which is in the hyperspectral wavelength. And then we are going to talk about thermal infrared. We'll see the difference in terms of how some of the sensors are based on solar radiation, reflectance of solar, and others are based on thermal emission. So we will go into the details of making the distinctions between 2 or 3 of these. But essentially, these 2-3 different sensors are going to be useful for some of these use cases, but also lots of others. right? So material composition of surfaces, to understand what kind of material is used in a building, or in understanding. Harsha, my colleague, later will talk about using solar panels and understanding the potential to capture the PV, calculating those as well. So moisture at the ground surface, understanding soil moisture on the ground, thermal emissions and heat measurements. So not just picking up heat sources, but actually understanding the temperature through thermal infrared capabilities. So understanding the heat measurements as well. And then chemical signatures in soil. Whether it is whether the soil is has sufficient NPK, as under irrigated, over irrigated, so whatever might be the signature, or just a stressed soil, and consequently stressed crop. Understanding those different characteristics of both soil and the crop, building those signatures, which a human eye can't see, but through these narrow bands, hundreds of bands, narrow wavelength, hyperspectral, contiguous data, one is able to not just see, but build the signature so it can be automatically detected. And then obviously burn scars and so forth. So the whole idea of using these newer sensors is not to see once something has happened, but to see before something happens. So that's been the kind of distinction between using an optical and using some of these sensors to be preventive or early warning focused rather than reactive. So why do we do this from space? So why these sensing from space? Now, clearly there are some limitations. So if you think about it, as I mentioned in the first slide, field survey and ground inspections, right? So that's very infrequent. One needs to be able to do that regularly to stay on top of the ground reality or the situational awareness of the asset or the land, if I may. So that's one big issue in terms of non-space. What happens today in ground sensors, not very scalable. Bahrain is a small country, so potentially that can still work. But very large countries in ground sensors don't work, but also flying drones and aerial. And sometimes when you think about it in current context, geopolitical context, and that is also not a very good idea, right? To talk about drones and aerial. So space will continue to be a safer domain, whether it is peacetime or wartime. So that's another consideration, on hindsight. So field survey is infrequent, and obviously when you use capability from space, it's on demand and in real time. So there is no line of sight requirement. There's no denied environment. You can't use drone and aerial at will. There is a lot of regulations that applies to it, or even using in-ground capability, in-ground sensors. So that's on demand in real time, 24/7, whenever you need, so long as the particular sensor has the ability to sense through the night and through the cloud and through different weather pattern. The second is high operational costs. Obviously, when you have larger projects, your costs are going to be high because it's a large area monitoring through traditional sources, whereas from space, today we are talking about the smallest footprint of collection can be as small as 20-25 square kilometer, and it can go as big as we just recently submitted a tender for a government. We found a very large state has so many passes per day, 36,000 square kilometer can be collected in optical. Just in optical, 36,000 square kilometer per day of collection. So it's a very large area of collection that is possible today. with multiple passes that's happening with different sensors. Coming to the kind of sensors we are talking about, most sensors are doing daily revisit or every 2-day revisit. So these sensors we are talking today are not your very high revisit optical or SAR sensors. As you know, optical and SAR sensors have sub-daily revisit in most parts of the world, including Bahrain. But the sensors we are talking about today generally typically tends to have at most a daily revisit and at least every 2 to 3 days, which for the kind of use cases we are talking about, still good enough. But these sensors in these constellations will also improve moving forward, because hyperspectral and thermal are just coming into market in a very big way, commercially speaking. Just like what SAR was. SAR was 5 years ago, hardly much SAR was there. SAR was every 2-3 days. Even though it's 24/7, you did not have daily revisit of SAR. But now you have sub-daily. There are places on Earth, on the Eartheye platform, SAR can be collected something like 12 times a day, 24 hours, so every 2 hours. So that's kind of how SAR has come to the mainstream. I expect the same to happen with hyperspectral. Infrequent information updates. So that's obviously one of the limitations of non-space, because again, driven by traditional methods, which is not frequently updating, whereas in space, you can set and forget. You can set and forget for daily, sub-daily. I mean, as I said, sub-daily is not yet there for these sensors we are talking about today, but let's say weekly. You want hyperspectral imaging in certain bands for certain use cases to be done weekly. You can set and forget, and every week it gets delivered. Remote area accessibility is obviously is a case. May not be a big issue for Bahrain. For large countries, that is a huge issue, remote access. So again, space provides that, that removes that barrier to remoteness. But you might still have, even in a small country like Singapore, we have a customer who is collecting a construction on a weekly basis, but they can't use drone or aerial because that construction site, it's about 1 square kilometer construction site, but it's right next to the airport and an army base. So you obviously can't fly drone and aerial. So the only option is very high, very high resolution, like 15 centimeter optical data that they collect to understand the construction change. But again, hyperspectral could be one of those they could be using, or anyone also could be using in a construction monitoring to understand different material being used and the changes that's happening on the construction site. We'll talk about that as we get to the infrastructure use cases. Human-centric, and obviously that's prone to errors, and we all know that, whereas space data, it's geospatially more accurate and precise. So these are some of the reasons why these sensors are starting to appear in space, and providing the situational awareness for early intervention. So how do these technologies work, right? So as I mentioned, hyperspectral, short-wave infrared, SWIR, or thermal infrared, they access a wide spectrum, and let's look at those wide spectrum. So we are all very familiar with visible range. So that's your typical RGB near infrared. So RGB 400 to 700 nanometer. Then we go into hyperspectral 400 to 2500, SWIR 1000 to 2500, and then thermal infrared. So it kind of gives you the idea of where each one of them sits, right? So kind of SWIR sits between the reflected solar to thermal emission. So if you think about thermal, TIR is completely thermal emission centric, whereas your visible and near infrared is more reflected on solar radiation, and SWIR kind of sits in between. So it's a very interesting capability from shortwave. But shortwave, as you know, it is not thermal. It is part of the hyperspectral. So hence you're seeing that range from 400 to 2500 hyperspectral, and SWIR goes from 1000 to 2500. And in terms of understanding the hyperspectral capability itself, very similar to optical. It's based on reflected solar radiation, so primarily works during daytime. SUR has been used at night, can work with sort of some low light, like moonlight and so forth. Not great, but still works. But unlike thermal infrared, it's used heavily during night as well as day. So SAR and thermal are very useful for night collection, whereas SUR can also be used, but mostly still depends on a high illumination like solar. Sunlight. So as the picture reflects, reflected energy, and then you are collecting across hundreds of bands, very narrow contiguous bands, often going from 1 to 2 nanometer across hundreds of bands. So unlike multispectral, which is fragmented or discrete, whereas hyperspectral, as you know, it is continuous. That's a fundamental difference. So hence you might get, 8 to 12 bands of multispectral within the 1,000 nanometer range. In the VNIR, in the VNIR range, you may get up to 1,000 nanometer or 800 nanometer of up to 10 bands. But as you go into hyperspectral, the same 10 bands has now become hundreds plus bands, up to 100, 800 to 1,000 nanometer. And then as you cross over going into the 2,000, 2,400, 500, you're getting into the SUR range. So that's essentially how that the spectral resolutions is mapped out in terms of contiguous. So what happens is you get that data through the same ground station method, but then you're putting the data through because it's not visible, right? So it has narrow wavelength, but they have a lot of information contained in that. So what tends to happen is you either build some indices. We'll talk about some indices that are interesting indices that can be built on hyperspectral, including SUR and thermal, but also build models, inferencing models that are machine learning, deep learning based, where you train the data, the spectral signatures for automatic detection. All right, whether it is crop stress, whether it is soil condition, soil chemistry, or could be any of the other water quality and so on and so forth. So how do these sensors differ from others? So I think we kind of touched on some of those. So just to sort of summarize that, we all know optical. We are all big users of optical. As I said, it's limited. They are discrete, whereas hyperspectral, hundreds of contiguous. SUR falls within that hyperspectral. In terms of typically 50 to 200 bands, 1,000 to 3,000 or to 2,500 nanometer wavelength. So that's been the kind of SUR capability. Thermal, as we discussed, can go between 8,000 to 14,000 nanometer, and it's based on emission detected from Earth. And then SAR and INSAR. I thought just for comparison's sakes, we put optical and SAR on either end of these three sensors we are talking about today. So SAR, INSAR, you have these X, C, L, and P band as well. So 4 different SAR bands. Polarizations can go from single to quad pol. Based on the polarizations, you have different use cases that come into play. Similar to SAR is thermal. Can be imaging at night. So those are the kind of the night hawks, night vision. And then you have the energy source, as we already discussed. And then the kind of information that can be gathered from them or in terms of use cases, right? So that's how the different sensors are starting to work together in today's Earth observation. So it's no longer optical or SAR or hyperspectral. It's all of them. I like to call it horses for courses, depending on the use case. Either it's a single sensor, single data, or multi-sensor, multimodal. You bring these different data sets together to unlock the information that's contained in them. Yeah, so we have interesting use cases where you can combine with an optical with SAR, but also a thermal with optical as an example. Right. So this is kind of giving the spectrometer view of what those wavelengths break down to, and then what the kind of use cases. So this is, we are going to go into the detailed use cases. This is just giving at a very high level. Where do you use these different sources we talked about? Where do they apply, right? So hyperspectral, crop disease, nutrient stress detection, we talked about in PK deficiency or crop stress, understanding vegetations, not just knowing its vegetation, but knowing rice versus soy versus some other crop, right? So it's really discriminating discriminating different types of vegetation, which is very hard to know from optical data. But even with not very high resolution hyperspectral, even at 5 meter, 10 meter resolution data, you can discriminate species, crop species or forest species in a forestry context. Sewer, as I mentioned, flood-led pollution detection. So post-flood understanding pollution, which I understand is sometimes a problem in Bahrain. Camouflage, understanding vegetation versus camouflage. So security use case. Soil disturbance, soil moisture, understanding water stress, and construction, right? So there is always a signature and that is around construction, a new construction versus an older construction. Thermal, big usefulness is around heat island, detecting heat island. LST has been traditionally used, land surface temperature, but heat island is particularly using long wave infrared. So thermal, if I break it down, you have medium wave infrared and long wave infrared. And the medium wave is kind of sitting between reflected solar and thermal emission, because SUR is closer to the VNIR where it's reflected solar, whereas MWIR is both reflected solar and thermal emission, whereas LWIR, long wave infrared, it's exclusively thermal emission. So it's only sensing temperature. So hence urban heat, surface temperature, LST, and so forth. Whereas the MWIR, which operates in 3,000 to 5,000 nanometer, very good at detecting fires and nighttime as well, right? So nighttime thermal imaging happens with MWIR better than LWIR. So that's kind of how thermal TIR or thermal infrared is into two separate buckets, medium wave and long wave. So yeah, so those are some of the use cases around that. So on the Eartheye platform, just to talk about, we're talking about different sensors, the use cases, but where do they exist? What are these commercial data sources for these different spectra, right? Whether it's hyperspectral, shortwave. So on the Eartheye platform itself, just very quickly before we go into use cases, so you can connect the dots. The highest resolution hyperspectral in the market today, commercially speaking, is 5 meter resolution, and it goes up to 10 meter. And on the platform itself, there are multiple hyperspectral sensors going up to hundreds of bands. all the way up to 2400, 2500 nanometer. Then there is a shortwave, which is part of hyperspectral. We are calling out separately. That's in 10 meters. So 10-meter shortwave in 450 bands. So in the 450 bands plus hyperspectral, there is a 50 to 100 bands shortwave in 10 meter. So that's another very interesting capability with the every 2A revisit. And then there is the thermal infrared. We just talked about the medium VNIR resolution speak, medium resolution VNIR 10 to 30 meter to high resolution LWIR 25 to 70. And then there is also very high resolution MWIR coming up in mid-26. That is at 3.5 meter. So think about detecting fires and nighttime thermal imaging in MWIR at very high resolution of 3.5 meter will be available in mid-26. Right now on the platform is VNIR and LWIR. And so how do they fit in with the rest of the sort of multimodality or multi-sensor Earth observation? You think of them as, you use optical or multispectral, SAR, full motion. These are the sensors that coexist with the rest of the sensors. So again, horses for courses. If you need a specific sensor, which is one of the three we just talked about, then they get used. We're calling out greenhouse gas separately here because that is also a type of hyperspectral sensor. Within the hyperspectral bands, you have the greenhouse or methane emission bands, particularly tuned. So there are methane instruments in space, which are hyperspectral instruments, but they are tuned for detect methane emission, particularly methane and CO2, but they also operate within the hyperspectral wavelengths. So these are the sensors on the platform, in addition to the ones we talked about in optical and SAR and the rest of it, right? Yeah. So they can be, the point here is they can be combined with other sensors to collect data over a location of interest or over a situational awareness of interest, or they can be tip and cued combined across two different sensors. The first sensor will pick up some information, such as a thermal infrared in the night will pick up a heat signature. And then in the day, an optical very high resolution will start prosecuting that as just as an example of tipping and cueing between thermal and optical or thermal and SAR and any of those combinations. So one of the capabilities that exist on the Eartheye platform is to how do you get these data to work together, but also deliver the information, not just the data. So when you task, you get the different sources over your area of interest, but also to then extract the information of interest, which is the kind of use cases we are going to be talking about. And the platform itself works like a self-service e-commerce platform. I don't want this to be a sales pitch, so I'll just go through it very quickly. So you can task and you can attach an index of interest to you, any indices. Harsha will talk about what these indices can, how they are valuable when you build indices in the invisible bands, how valuable they become. But also there are machine learning models. For example, one of the models we are releasing very shortly is to detect tuna. So tuna fish stock. Right, so in the waters, to understand the tuna concentration using hyperspectral data. So those are very interesting machine learning models that are built to deliver different use cases using hyperspectrals for thermal for the users. So those are what we call feeds, and then just like Uber, you pay as you use them when you get the data and when you get the information on the back of the data, which is called the feed. So feed gets delivered within a few minutes of the collection of the data. And then you receive on the platform, or you can also receive the data and the information, i.e. the feed. We'll talk about what these feeds are over at your own target location. That could be your own geospatial platform, your own GIS environment, and so forth. Right. So as I mentioned, speeds are both indices and machine learned inferences, right? So it could be simple thing as crop health, nutrient analysis, NCCI. So there's an index called NCCI or NDVI. You're all very familiar with NDVI, NDRE, but there are also lots of other different indices that are built with hyperspectral and thermal data, which Harsha will talk through. And then, as I mentioned earlier, one of the new models we are releasing is tuna fish concentration. So detecting tuna in open waters. So detecting fish stock and then detecting specifically kind of bluefin tuna. So that's a machine learned model with hyperspectral data. And Harsha can explain if you're interested to know how that was developed. So these are some of the indices. So built along hyperspectral, SWIR, and thermal infrared. So NDVI and NDRE is something you're familiar with, but there are also other indices that are based on thermal. And so I will hand over to Harsha to start on this slide and walk through the rest of the segment with the specific use cases, because the next segment is the real world applications using these three data sets.
Starting with this slide, as Shankar has already introduced about hyperspectral, SWIR, as well as thermal imagery. In the next few slides, I'll walk through the various domain-specific use cases for hyperspectral imagery, SWIR band and thermal imagery, and to understand what makes them unique for the real-world application. We'll come back to the indices slide later. So, Shankar, can you move on?
Yeah, I'm on the what next slides.
Yeah. So we will be going on to understand what makes them unique for the real world applications. So starting with the urban development, next please. Starting with the urban development today is highly challenging, especially due to rapid population growth, extreme heat conditions, limited freshwater resources, and restricted land availability. And also rapid urbanization growth has led to the traffic congestion, higher pollution levels, and reduced green spaces, and that also affects our environment. So given these challenges, there is a clear need for a well-planned, resilient urban structure that ensures efficient resource use, environment stability, and an improved quality of life. This is where this technology comes, like hyperspectral and infrared remote sensing, plays a very crucial role in this area. So, for example, hyperspectral, when extended to SWIR bands, gives a unique fingerprint for each material, which helps to identify what type of material it is. For example, roofing materials, or what type of roofing materials it is, what is the coating and urban surfaces across the entire city. We can detect the damage also about the roofing conditions, as well as the like corrosions or any other damages using the SWIR band. For example, for a solar panel installation, we need a very clear space. Clear space in the sense there will be no obstacle around it, no trees, no shadows, and the area must receive maximum amount of heat, sunlight during the day. So in that condition, when we look the surface from the above, we can find such an area which is very clear and which is very best for the solar panel installation. In this scenario, SWIR bands or hyperspectral bands gives us the location that is pretty clear, and the thermal imaging helps us to find out which area receives the maximum heat during a day. So in that way, we can plan which area is suitable for the solar panel installations. Going on to the urban heat island detection, as Shankar has already told, urban heat is a major challenges nowadays. Due to rising the temperature or industrialization, urbanization, the cities are experiencing more heat buildups because of the concrete structures as well as the reduced green cover. So in that case, thermal imaging can help us to understand which is the major hotspot area, and using the reflected thermal energy, we can find out that, and then we can later plan what we can do, how we can control the heat emission. Like we can use reflecting mirrors, we can use coatings, we can different precautions, different steps we can take to reduce the urban heat. Also, with this increase in population, traffic is a big issue. Sometimes traffic occurs due to the road conditions also. So in that case, hyperspectral with the SWIR band can help us to understand to the condition of the road due to which this traffic congestion is happening. So these are the applications of urban thermal as well as hyperspectral with SWIR or band remote sensings, which can help us to make a well-planned urban as well as which provide a good quality of life for the people. So moving to the next slide.
So Harsha, before we move to the next slide, one of the questions asked when you were away was what kind of liquids can be identified. So I gave an example of oil and types of oil. Is there anything else? The question was what liquids can be identified on Earth with hyperspectral, on ground, sorry.
It depends on the chemical composition of the types of the materials. For example, oil are different types, as well as different hydrocarbons can be found also.
Hydrocarbon.
Different types of hydrocarbons we can identify with that, like kerosene, and different types of things we can find out.
Okay.
Since moving to the next domain, that is environmental safety. So expanding from the infrastructure, hyperspectral data plays a critical role in environment safety and monitoring also. With this urbanization and increasing population, many environmental challenges are emerging these days, including coastal pollutants as well as greenhouse gases. So in case of, for example, coastal pollutants, so coastal areas are affected by oil spills or industrial discharge of water dumping, waste dumping. So hyperspectral images help us to identify these sources as well as the extent they are disrupting our environment, marine environment. Industries also release gases, or many gases are released in that way. We can use thermal images which help us to detect how much greenhouse gases are generated from an industry, as well as hyperspectral satellite-based sensors can help us to understand, can help us for continuous monitoring of the environment and these greenhouse gases. So we can tell how much is the quantity right now, how much is increased after a few days. So all these monitorings, this hyperspectral and thermal imaging, we can help us, and they can tell us how much is we can have a continuous monitoring of these gases and pollutants. For example, and one application is oil spill. So we can detect oil spill. We can detect the extent of the oil spill using hyperspectral imagery. In fact, with any optical sensor, we can detect the extent of the oil spill. But what hyperspectral provides us is not only the extent of the oil spill, what type of oil spill is there, and as well as when there is an oil spill in an area, the water quality is also getting affected, and the environment is also getting affected. So using hyperspectral imagery, we can tell us, or it gives us a spatial extent of to what extent water quality has been affected in the surrounding areas. So these are the applications of hyperspectral imagery and thermal imagery in the marine application, as well as one more thing I want to add, microplastics. As I've already talked about microplastics, it is very harmful during these days, and the amount of microplastic is increasing in the oceans. So hyperspectral imagery as well as the thermal imagery can tell us what type of, especially hyperspectral imagery with the SWIR band can tell us what type of plastics are there, what are the extent, and where the accumulation zones are there, as well as the source also. So from where it is coming, if there's an industrial discharge, from where it is coming. So this all, the power of hyperspectral imagery is we can not only get the extent or the material, we can also identify how much is the extent of the how much it is getting affected, and how, to what extent in an environment it is getting affected. So these are the applications. So this all will provide us to take active response to environmental threats through hyperspectral imagery and thermal imagery. So moving to the next slide. Agriculture. The way agriculture is practiced varies from place to place. That is maybe due to the difference in the soil quality, water availability, and local climatic conditions. The sandy and saline soil, high temperature with low rainfall, usually affect the traditional farming practices. So as a result, we need to plan a agriculture practice in a controlled environment with efficient irrigation method, with efficient nutritions, and we should adopt such a method that should not degrade our soil quality, that should not impact our environment in a long run. For that, hyperspectral imagery plays a very important role in identifying soil fertility mapping. With the hyperspectral imagery and SWI band, we can tell us uh, what is the quality of the soil, how much is the nutrient, what are the nutrients that the soil is lacking. That will help, instead of using over fertilization, that will help us to take a precise action, and that will provide site specific information that will help us to take a precise action. Same for crop disease detection. There are many losses due to crop diseases, and when the symptoms are shown, precautions are taken, steps are taken, it's already been delayed. Sometimes it's too delayed, that due to which great loss of soil, loss of crop is there. So in that way, in this scenario, hyperspectral helps for early crop detection a lot before the symptom appears. So we can take necessary actions. In case of this, one more example for thermal, I want to say thermal helps us to detect the crop water stress. Crop water stress, for example, I'd like to give a small example. For example, a leaf, when it is a water stressed or water scarcity is there, leaf closes its stomata. In that case, to avoid evaporation. So in this, evaporation is not there, as well as the heat exchange between the leaf and the atmosphere is not there. Not happens, that is transpiration is affected. In that case, heat is absorbed inside the leaf. That increases the temperature of a leaf. And with thermal energy, we can detect this temperature and find out, okay, the crop is under water stress. Not only this, the thermal imager also helps in drought conditions and in soil moisture. So using these methods, like fertilization, also these sensors also can help us to know how much carbon is stored in a plant as well as in a soil, and what is the issue. Sometimes what is the issue that there is a lack in the carbon holding capacity of soil or crop. That is not typically visible through normalized or optical remote sensing, but through hyperspectral we can get to know. So that will help in carbon sequestration and will help us to adjust the emission of the carbon in the environment. And we can take effective measures to reduce impact in the environment. Therefore, like technology-driven farming ensures productive agriculture systems. Like one more thing, when we use hyperspectral imagery for soil fertility mapping, we are using fertilization to improve the productivity of the crops as well as the yield prediction. Uh, in that case, when we are using over fertilization, it may help in the small run, but in a long run, it will degrade the quality of the soil. So, hyperspectral remote sensing helps us to understand what it is actually needed by the soil and what time. Then one more point is yield prediction. How we can predict yield. So when we know the condition of the crop with indices is a excellent method to help us know the condition of the crop and help us to predict what will be the what will the yield after the end of the cropping. So in this way, both hyperspectral and thermal imaging helps a lot in agriculture. Next slide. So this hyperspectral captures the detailed spectral signatures of water constituents as well as the materials, which we call a fingerprint, which we can say as a fingerprint. So every material has a unique fingerprint, which helps to identify which type of material. This is helpful, especially in the detection of dark vessel material when the AIA support system is off and we want to know where is the vessel. In that case, we can use hyperspectral remote sensing to find out where is the vessel is. Also, uh, in case of illegal and overfishing, since we can find out the materials, we can tell, okay, this is the illegal ship or something illegal is happening since the AIS is also off. Fish stock detection, we already did tuna fish stock detection. Since hyperspectral and thermal hyperspectral especially gives us the complete system of the water, complete constituents of the water, we can understand what the fish actually needs. For example, fish usually goes where the food is there. It's a food web. So we can find out where the food is present at that particular point of time. And then we can estimate the fish stock in that area using hyperspectral remote sensing. And oil spill detection is already possible with hyperspectral remote sensing with the SWIR bands. So our next slide. Also, hyperspectral satellite data supports the entire marine life, from mineral exploration to environmental monitoring and sustainable closure. In a mining area, only the what type of minerals are present is not important. How the mining is affected to the nearby areas, to the how the land surface is changing, and what is the impact of that particular thing in the environment. These are also taken into consideration. In that scenario, hyperspectral remote sensing helps us to find out what type of rock or mineral is there. And thermal imager can help us to find out whether any mineral is there or not. And hyperspectral can tell us what type of mineral is present in that particular area. As well as when we go for um, uh, land changes. So this sensors can help us to detect how the land is changing, what are the emissions, how much emission is there, and how that emission is affecting the environment. Tracks vegetation regrowth and land recovery from mining activities, as well as identify the contamination, whether it is water or it is land, and how the changes are happening. So that is like mining safety monitoring and mining rehabilitation. That is how changes are there and what should be taken, what is the impact of those changes in the environment. Everything we can access to the hyperspectral and thermal remote sensing. Next. Defense or security is another important area. Um, Hyperspectral remote sensing can tell us what type of material is there. So we have different targets of materials and we can find out what type of materials that is called target detection and tracking. As well as um, border security and surveillance, detection of hidden and camouflaged assets. Since SWIR band can tell us what type of material is there, we can also detect whether it is hidden, what hidden material is there, or camouflage assets. We can understand the chemical compositions, for example, chemical, biological, or radiological compositions that can help us to understand the like we can nuclear detection and we can have a continuous monitoring from the space. From the space, we can have a continuous monitoring of a border security, border area, target. We can direct targetation how the movement is happening from one place to another place. These structures, these materials are complex, have complex spectral signatures, like mine, underground mine. They have complex signatures which we detected, and we can help. And hyperspectral remote sensing can help us to understand what it is. So this helps to um, detect unauthorized accesses and reverse the hidden materials based on the spectral signatures. Next.
Yeah, one of the things I would add on is particularly in the defense context is picking up heat signatures using MWIR, medium wave infrared heat signatures from assets, defense assets, whether it's missiles or any other signature in a very high resolution, right? So we talked about 3.5 meter resolution MWIR, which is going to be very helpful both in day and night to detect this thermal signatures that can be attributed to heat emissions, not just solar radiation, reflected solar radiation, but also heat emissions from any of those defense apparatus, such as missile launch, as an example. So I think that's going to be very, very critical moving forward with very high resolution MWIR. Yeah. Right. Anything else, Harsha?
No, Shankar.
Okay, great. Thank you. So with that, we kind of went through all the different use cases organized by different domains or themes. So essentially, you saw the view of climate, environment, infrastructure, agriculture, and urban planning and so forth, and the slicing or the application of hyperspectral, including shortwave, infrared, SWIR, and thermal. So that's what Harsha walked us through. So I wanted to, this one of the segments that Rasha had asked us to cover is software and data access overview. So how do you get access to all of these different capabilities? So clearly you have open source, just like in optical, you have Sentinel-2, Sentinel-1 for SAR. You also have, in the world of hyperspectral, SWIR and thermal, you do have open source data. They suffer the same fate as the open source optical and SAR Sentinel-1 and 2 suffers, which is the temporal resolution or the cadence, as well as also the resolution, right? So as a public good, open source, they are very good, they are useful, but they have their limitations. So some of those data sources for hyperspectral are Nmap, Prisma, Emit. Not sure if any one of you are using them. Obviously, Sentinel-2 has SWIR bands, and then Landsat 8 and 9 as well, including Aster. Thermal infrared, most people use MODIS and VIRS, so quite well known, but also Landsat 8 and 9. And how the licensing works, you already know it's open source. Typically, it's processed in-house. Some post-processing has to happen in-house, and the use of GIS is typically how people would consume that sort of information, I would presume. The commercial side of things, as we discussed previously, hyperspectral, SWIR, including thermal, medium wave, long wave, are available on the Eartheye platform. They are commercial. but they're available as a single government agency license, whole of government agency license, but are also available CC BY, which means you can publish them on a citizen-facing website. So different licensing constructs are available for these different sensor modalities. Information is automated. There's no human in the loop. On the Eartheye platform, whether it's an index or whether it's a feed, it's automatically extracted from the source or from the sensor data, whether it's hyperspectral, including SUR, thermal, or any other, for that matter, optical, SAR, and so on and so forth. The software used is the Eartheye platform itself, but we also have users who take the data and the feed into their GIS for further analysis. And we deliver the data directly to, the Eartheye delivers the data directly to the user's GIS environment.